Chapter 17, Complex Numbers. This is the chapter where we learn what we're going to do about these pesky square roots with the negative inside. And this also applies to any other even index radical, fourth root, sixth root, and so on. And the big surprise is we are simply going to take the negative in the square root and replace it with an I. So it seems sort of a cop-out, but what we've done here is we're basically going to define a new type of number. Okay, so in the case of square root of negative 4, what we're doing is we're separating away the negative 1 from the 4. We're separating them like this. And the square root of 4 can be calculated now as the principal square root, and we get a 2. And the square root of negative 1 is just simply going to be replaced with an I. Okay. Now, I it's still a different type of number. At least we're not just simply throwing up our hands and saying, hey, that's not a real number. We're giving it a name, and this 2i here is a complex number. And the I is a lot easier to manage rather than a bunch of square roots of negative numbers floating around. So it's a little more convenient, but you can see here that defining this new type of number, complex number, it has a particular structure. We have the structure or the format of a complex number as A plus the BI. Okay, and the BI is the imaginary part. So what you see here is numbers that we're used to dealing with, multiplying together, squaring, taking square roots. Okay, real numbers, a real part plus an imaginary part. Okay, the BI is imaginary. Alright, now that we've sort of given ourselves an easy way to at least manage complex numbers, we need to define what it means to square an imaginary number, because this is going to pop up a lot, especially in this chapter, since we're going to talk about adding, subtracting, multiplying, and dividing complex numbers. And the definition is simply I squared equals a negative 1. And the way you have to look at this is that if we consider I squared, and then we say, well, we have defined I as just simply the square root of a negative 1, then if we replace I in this exponential expression, then we have square root of negative 1 squared. And so we look at this as the square and the square root are going to knock each other out, and all that's left is a negative 1. So this A plus BI is the standard form of a complex number. And so from now on, whenever you have a square root or a fourth root or a sixth or so on root with a negative inside, then you're going to drop the negative from inside the radical and simply write it as an I. So originally, if you look at this example that we were given, 3 plus I squared of 5, this could have originally been written as a 3 plus square root of negative 5. Okay, so we prefer this way with the I in front of the square root symbol, not with the negative inside the square root. Okay. Bottom of the page, example 1 wants us to show that 3i and negative 3i are solutions to the equation x squared plus 9 equals 0. So this type of equation, when we ran into it back in chapter 5, well, let me see. maybe it wasn't chapter 5, but we at least ran into at some point this x squared plus 9, and we said, well, x squared plus 9, we're solving a quadratic equation, so we want to try to factor it, and maybe you tried to factor it this way, but if you do that, then when you multiply it back together, you see that this doesn't actually work. If you full x plus 3 times x plus 3, you get an x squared plus 6x plus 9. And so this isn't a legitimate way to factor that. And the x squared plus 9, we said it was the sum of squares and it couldn't be factored. So we were kind of stuck not being able to factor this piece in the way of solving this quadratic equation. And there's another way you could go about it. You could separate the x squared and the 9 by putting the 9 on the right hand side, but then it becomes a negative 9, and then you could say to yourself, we'll take the square root of each side, but then you see that on the right hand side we're taking the square root of a negative number, and that's not to mention that we're supposed to put a plus and minus in front of the square root. So either way, we were sort of stuck, but now we know how to handle these negative ones inside of a square root. And we're going to see that the solution to this equation is not a real number, but these new types of numbers that we're talking about, complex. So to check 3i as a solution, we just replace the x with a 3i and we square it. We'll get a 9, and an I squared plus a 9 equals 0. And then according to our definition up at the top, I squared is a negative 1. So they're interchangeable. Okay, replace the I squared with a negative 1, and we get negative 1 times 9 is a negative 9 plus a 9 equals 0. So now our equation checks out. We check the other one, and we have a minus 3i squared plus a 9 again, and if we square a negative 3, we get a positive 9 and an I squared. Alright, I squared is a negative 1, so this 9i squared becomes a negative 9. We add 9 to it, we get 0. So as long as we use our definition from up top, I squared equals negative 1, then these two complex numbers here are solutions to our equation. Here we have a diagram that's sort of breaking down all the various numbers that we've talked about throughout algebra, starting in intro algebra. We see that here real numbers can be also written as a complex number. It just simply has a 0 imaginary part, and then from there inside real numbers we have rational and irrational, and then we go all the way down to the very first type of numbers that we probably started talking about in our first math class, natural numbers. Okay, so this sort of explains all the different types of numbers and how they're related. But on the next page, just like real numbers, we can also add, subtract complex numbers. So example 2, it wants us to write 3, which is real. Okay, if we just write 3 down, there is no I, and so we can interpret this as a real number, but at the same time we could also write it as a complex number with a 0 imaginary part. simple to add and subtract complex numbers. What you have to do is just simply look at the I as if it were a variable and add them that way. You could talk about adding complex numbers as in adding the real parts and then adding the imaginary parts and break it up this way. And in that case, we just simply pluck out the -2 and the 6 and add those together. And then we pull out the 5i and the -i and add those separately. And again, you interpret the I, or you treat it as if it's a variable. So our real part when adding these two complex numbers would be 4, and the imaginary part would be a 4i. Okay, so what we have here is inside this first set of parentheses we have a complex number 1, and then we've added another complex number to it, complex number 2, and what we got as an answer turns out to be also a complex number. Alright, so just treat the I as if it were a variable. So here we have a 7 and then plus another 7, and so we end up with a 14. Then we have a -I plus an 8i. We end up with a 0i. This can still be interpreted as a complex number, but we can also call this a real number as well, 14. Okay, subtracting. Basically, what we need to do differently is we need to say we're going to distribute this negative throughout this second complex number. So we can write all this out without parentheses as long as we interpret this as a -6 and a plus I. So this minus times that minus gives us a plus I. Alright, so what we do at this point is we take the real parts, -2, -6, and we go over here and we say that equals a -8. We take 5i and a plus I. 5 plus 1 is 6, so we write 6i. Okay, we don't drop the I here. You have to keep up with it. And this -8 and 6 cannot be combined, just like if it were a -8 and a 6x. Of course, this is a variable that represents an unknown number, but I is just a different type of number. But you treat them as if they were variables when you add and subtract them. Alright, this next one, we have, again, one complex number, subtract another one. So we distribute this minus here to the 7 and the 8i, and we get a -7 and a -8i. If we look at the real parts, +7 and -7, we get 0 for the real part of the sum, and then if we take the imaginary parts, -8i and +8i, they basically cancel out. Or no, I'm sorry, they don't cancel out. They double, and we get -16i. Okay, and this is referred to when you only have the imaginary part of the real of the complex number. You can refer to it as a pure imaginary number. So at the bottom of the screen, we've talked about addition and subtraction. They're pretty straightforward. But now for multiplication of two complex numbers, if you look at them, of course, they sort of remind you of binomials. And just like binomials, when they're multiplied by each other, we have to use the full method. And so that's exactly what we're going to do with these two complex numbers here that are multiplied. We would take -2 and distribute it throughout this second complex number. So we would write -2 times 6, and then we write -2 times a -I. Alright, our next term in our product would be inner and last. 5i times 6, so we write plus 5i times 6. And then we have another plus 5i. We just distribute this 5i throughout the second complex number. 5i times a -I. Okay. And so we have 1, 2, 3, 4 terms. Now we want to go back and clean it up. -2 times a 6 is a -12. These two terms in the middle are both imaginary parts, so we can add them together. We have a 2i minus minus, so it's a positive 2i. And then we have a plus 30, 5 times 6, I. And this last one is going to end up giving us a minus 5, because the I had a minus in front of it. And it's also going to have an I squared. So if we take another pass through this expression here, we can, 1, combine the imaginary parts. 2 and a 30 would give us 32i. And then for this last term, we can replace the I squared with the -1, and so that now it becomes a real part of our complex number. We have a -12, and here we have a plus 5. So in the end, we get a -7 plus a 32i. Alright, example 8 wants us to verify that -1 plus I square root of 3 is a cube root of 8. Alright, so in other words, we said earlier, if we cube a 2, then we get 2 times 2 times 2, and that equals 8. So 2 must be a cube root of 8. Likewise, if we can cube this complex number that we're given, -1 plus I square root of 3, and we can get 8, then it also has to be a cube root of 8. So we'll write this out, and it's a cube, so we have to write it 3 times. And now we're going to go about multiplying these together. Alright, so we'll take 2 at a time, and I'm probably going to run out of room here, so I'm going to have to erase some of this. Just multiplying these first two, I would have a -1 times a -1, which is a +1, a -1 times an I squared of 3. Then, okay, I've done these top two. Now I need to take I squared of 3 and multiply it times the -1 and then itself, and so I end up with another minus I squared of 3, and then I end up with a plus I squared and a square root of 3 squared. Okay, just this last term in the binomial multiplied by itself. Okay, this works out to be 1 minus 2I squared of 3, and then we have the square root of 3 squared, which would just be a 3, and the I squared would give us a negative 3. Okay, so I squared is negative 1, square root of 3 squared is a 3, so this last term simplifies to be a negative 3, and now I can combine this negative 3 with a 1 and get a negative 2. Alright, so that was just multiplying two of them together. Now we want to go back and pull over this last negative 1 plus I square root of 3. And once we multiply these together, this should all work out to equal 8. All the i's should disappear. So if we fold this, we get negative 2 times 1, or negative 2 times negative 1 is a plus 2. We get a negative 2 times I squared root of 3. Now we need to take the 2I squared root of 3 and multiply it by 1, a negative 1. We get a plus 2I square root of 3. This negative and that negative make it a positive. And then finally we have a negative 2I square root of 3 times I square root of 3. So we end up with a negative 2. I times I is I squared. And then we have a square root of 3 squared. Alright. Bring down the 2. We have matching terms in the middle with opposite signs, so they cancel. I squared is a negative 1, and square root of 3 squared is a 3. We have 2. Minus minus is a plus, and 2 times 3 is a 6. And so amazingly, we do end up with an 8. We cubed negative 1 plus I squared of 3, and we ended up with an 8. So this must be a cube root. So up to this point, we've talked about how to add, subtract, and multiply. And now there's only one left, and that would be divide. But before we talk about division, we have to define what it means to take the conjugate of a complex number. Alright, and it's super easy. The conjugate of the complex number just simply means you change the sign of the imaginary part. So, with example 9, this bar across the top of this whole imaginary number, or complex number I should say, 3 plus 4i, that's our complex number. But this bar tells you that you need to take the conjugate of it. And this requires really no calculation. You just simply change the plus in front of the 4i to a minus. Alright, it's not hard at all. You just have to recognize the symbol that's telling you to do this. Flat bar across the top of a complex number represents the conjugate of that complex number. So for conjugate of 2 minus 7i, I'd write 2 plus 7i. Only the sign of the imaginary part. Now, example 11, what we have here is a complex number times its conjugate. Okay, and something kind of special happens when you take a complex number and multiply it by its conjugate, and we're about to work that out here. So the way we could write this is a plus a bi, and then its conjugate for the second factor would be a minus bi. Alright, if we multiply these two together, we get an a squared. Then we get a minus a bi, okay, and that's from these two products, okay, the first term of the first binomial times the second binomial. Then we have the second term times the second, and I call that a binomial, but it's a complex number. We have bi times a, so this becomes a plus abi. And then for the last term, we just simply have a minus bi, and the b and the I are squared. Alright, and what you see happen is the two middle terms cancel out. So up above, we're left with an I squared and then a minus b squared, and the I squared can be replaced with a negative 1. So going even further, we still have the a squared, and then this minus changes the sign of the b squared and it becomes a plus b squared. And the reason why we work this out in terms of variables is because it doesn't matter what numbers a and b are. If you take a complex number, for instance, let me give you some numbers here so that this sort of makes sense. If you take a complex number such as 3 minus 2i, and you multiply it by its conjugate 3 plus 2i, then what you can do to quickly calculate this is simply take the numbers 3 and 2, add them together, or add the squares of the 3 and 2, and you've got your answer. It works out to be a real number, 13. Okay. So it's really just giving you a shortcut for multiplying complex number times its conjugate. And that's exactly what we have to do to divide two complex numbers. So as a definition for division, if we want to divide a complex number by another complex number, then all we really do is we take this complex number division, we go off to the side and we multiply by a fraction with the conjugate of the denominator, okay, the conjugate of the denominator in the denominator and the numerator of the fraction that we multiply by. Alright, now on the bottom you see that we have complex times conjugate, and so we can just replace that with the c squared plus d squared, and then on the top what we end up with is a real part, AC plus BD, and then an imaginary part, AD plus BC, with a sign of negative. Okay, so this is just in general how you divide complex numbers. So example 12 is telling us how, explain how we can use the results from example 11 when you are dividing two complex numbers. Well, it just gives us a shortcut. You can obviously see in the denominator of this division, it prevents us from having to use the full method. Okay, instead we can just pull out the numbers and square them and then add them. So here we have a complex number divided by another complex number, okay, a different one. So what we do is we don't change the way this quotient has been given to us. We go off to the side and we simply write the conjugate of the denominator on the top and the bottom of a fraction. The bottom is super easy to work out. We simply get 6 squared and then we get plus 1 squared. So the bottom is going to work out to be a 37. Now the top is where we actually have to do quite a bit of work. We're going to have to full negative 2 plus 5i and times 6 plus I. So our first couple products are negative 12, negative 2 times 6. Then we have a negative 2 times and plus I, so that's minus 2i. Then we take 5i and we multiply again the 6 and the I. We end up with a plus 30i and a plus 5i squared. Okay. We can simplify the top to a negative 12, a plus 28i, and a minus 5. Because the I squared is negative 1, this becomes a negative 5. Now the negative 5 can be combined with the negative 12 to give us a negative 17. Our imaginary part 28i. And at this point we can separate the real and the imaginary part by simply writing a 37 as the denominator of each. And so here we have our final result. This is the quotient of these two complex numbers divided. Alright, here's another one to work out. Okay, on the top we have 7 minus 8i divided by 7 plus 8i on the bottom. So we're dividing complex numbers, and all we need to do is take the denominator off to the side, write down its conjugate, and multiply the top and the bottom. Alright, the bottom is easy to work out. We have a complex number by its conjugate, so we just take the numbers and we square them and add them. A 7 and an 8, square them and add them. That gives us a 49 plus a 64 as our denominator. Now we full the complex numbers on top, because you can see they both have a minus. They are not conjugates anymore. So we full them and we end up with a 49, a minus 56i, and now we take the negative I and multiply it by the 7 and the minus 8i, and we get another minus 56i, and we get a plus 64i squared. We'll make one more pass through this numerator and simplify it. Minus 56 minus 56 is a, let's see, a 112i minus, and then we have a plus 64i squared, which would make it a minus 64. The I squared can be replaced with a negative 1, which makes the 64 negative. We can now combine the 49 and the negative 64 to get a negative 15. We'll write the imaginary part off to the side. And a 49 and a 64 ends up being 113. So we'll take the 113 and write it on the bottom of the real and the imaginary part, and we're done. So in the end, you want to separate the real and imaginary part to finish your division. Okay. Just like real numbers, sometimes we need to take the absolute value, which with real numbers just amounts to changing the sign sometimes. So for instance, real numbers, if I were to take the absolute value of a negative 3, I'd just drop the negative and write 3. Absolute value of 0 is just 0. And then if I were to take the absolute value of a positive number, it could be 4.15. There's no negative to drop, so we just write 4.15. Okay. Absolute value of a complex number is a little different. You can see here what we do is we have a little bit of computation, but we take the numbers of the complex number, for instance, of the 2 and the negative 7 as shown here, and we square them. Then we take the squares and we add them, and finally we take the square root of that sum. So in this case, the absolute value of 2 minus 7i ends up being the square root of 53. So it's definitely not as easy as taking the absolute value of a real number. There's quite a bit of calculation involved. Alright, but it is the square root of the sum of the squares of a and b. So absolute value of negative 2 plus 5i would be negative 2 squared plus 5 squared, which simplifies to square root of a 4 plus a 25, which in the end is written as the square root of 29. Okay, so it's definitely not obvious. Example 16, here we have 2 square root of 3 plus I square root of 5, so this is real and this is our imaginary part. Alright, so we pull out the a and the b, which in this case would be 2 square root of 3 for a, and we square it, and the b of the complex number would be square root of 5, and we square that. So we just sort of leave the I out. And what we do now is we go back and work out the radicand. 2 squared is a 4, and then the square of a square root just gives us the radicand, 3, and then square root of 5 squared just gives us a 5. So in the end, we end up with a 4 times 3, 12, plus a 5 square root of 17. So we've talked about how we simplify an I squared when we're dealing with multiplying complex numbers, and that is to just simply replace I squared with a negative 1. Alright, well, what happens if we end up with higher powers of I? Well, there turns out that there is a pattern Okay, for every 4, you increase your exponent, you repeat a same pattern, a same set of results. Now, here are first 4, 1, 2, 3, 4. Once we cycle through these 4, then those answers that we got for I to the first, I to the second, I to the third are simply going to repeat over here. Okay, for 5, 6, 7, 8. And then repeat again for 9, 10, 11, 12. Alright, I to the first power we just write as I. Anything raised to the first is just itself. I squared, we already know, it's a negative 1. But now, how can we simplify I to the third power? What we can do is write it as an I to the first times an I squared. Okay, these exponents, if we apply the product rule, these exponents can be added to give us the 3 back. So these are equivalent expressions. And breaking that up into an I to the first and an I to the second, we already know the parts. And so I squared is a negative 1, and then I to the first is simply just an I. So we end up with a negative I in the case of I to the third power. So finally, I to the fourth power we can write as an I squared times an I squared. Each I squared can be replaced with a negative 1, and so we end up with minus 1 times minus 1 plus 1. Okay, so following this same procedure, breaking things up into I to the first and I to the seconds, you could work out the rest of them if you wanted to, but as I said, they are going to follow this pattern: I, negative 1, negative I, 1. I, negative 1, negative I, 1. Okay, so I'll just pick one of these to simplify. Let's say we pick out I to the 7th power. We can break this up into I squared, I squared, I squared, and then that's 2, 4, 6, so we need one more I. Each I squared can be written as a negative 1. And 3 negatives multiplied gives us a negative overall, and so we have a minus I. Okay, and you can check any of these. Every increase of 4 repeats the pattern in terms of the exponent. Now, on the next page, what we're trying to do is speed up this process of simplifying I raised to a natural number. Alright, and they've given us this example here, and we're going to move away from simply using our definition I squared equals a negative 1. Instead, we're going to use this new result that we found: I to the 4th power equals a positive 1. And positive 1 is preferable because it doesn't matter what we raise a positive 1 to, it's just going to end up being a 1 again. So by using I to the 4th instead, all we really need to do is figure out what the remainder is going to be once we divide out these I to the 4th. Okay, so for instance, if we look at this I to the 53rd power that they've given us, then we say that 4 goes into 53 13 times and leaves a remainder of 1. Now, this 52 that's written here is just simply the 13 times 4. That's what 52 is. And so they've written it here, I to the 4th raised to the 13th power. Alright, so where does our remainder come into play? Well, our remainder is just going to sit off to the side right here. Alright, 4 has went into 53 13 times, and so that accounts for this part of the product here. Well, since this is based on an I to the 4th, it just ends up equaling 1 to the 13th power, which is just simply a 1. Alright, so however many 4's that you can divide out of your exponent, that just ends up being a 1, and you can toss them away. All you really need to do is focus on the remainder. Okay, once you have the remainder, you can just simply go and write an I with that particular remainder. Alright, and from there, if it needs to be simplified, you can revert back to using I squared. Alright, so hopefully that makes sense. If not, then we're going to work some examples. So we write I to the 34 in terms of I to the 4's. So how many I to the 4's can we take out of 34? Well, if we take out 8 of them, then we've accounted for 4 times 8, 32 of the original 34. Okay, because what we're doing here is we're applying the power rule, 4 times 8. That tells us how many I's we've used up. There is a remainder of 2. Okay, remainder 2. Maybe the R was supposed to go first, but this just simply means that we go over here and we write another I, but it's going to be squared. So we've accounted for all 34 of the original I's. This part here, that just ends up being a plus 1. And so all we really need to worry about is this I squared. Well, what is an I squared? It's a minus 1. So I squared minus 1 times a positive 1 gives us the simplified version of I to the 34th power. Alright, example 19. What we can do here is first apply the product rule, which tells us that we can add the exponents as long as the bases are the same. So we end up with a 77. Alright, we want to break it up into I to the 4th. And so how many times will 4 go into 77? We'll do a little long division here. 1 times 4 is 4. We're left with a 37, and then we can take out 9 4's from 37, and we'll have a remainder of 1. So over here we can write I to the 4th to the 19th power, and then we have 1 I left out to the side. We're just going to throw those away, and we're done. Okay, this is one of our basic results, and so I to the 77 is just simply an I. Okay, I to the 211 will go here. Divide 211 by 4. We get a 5. And then we get a 2, which gives us a remainder of 3. So R is 3. We're just going to throw that away, and we're going to write I to the 211 equals I to the 3rd power. I to the 3rd power is just a negative 1. So you have to sort of memorize those first 4 results that we came up with. I to the 1st power is I to the 2nd power is negative 1, I to the third power is a, well, uh, let's see, that's a negative I, sorry. And then finally, I to the fourth power is a 1. Alright, so I'm glad I wrote that down, because this wasn't a negative 1, it was a negative I. Okay. So our last example for this simplifying our exponential i's, here we have I to the 7th to the 6th power. We can apply the power rule and call this an I to the 42nd power. If we divide 4 evenly out of 40, then we just end up with a remainder of 2, I squared. 40 divided by 4 is 10, so we're left with an I squared remainder, and I squared is equal to a negative 1. So once you figure out that you just need to divide out 4 and keep the remainder as your exponent, this becomes pretty simple. Okay. Now, we are warned about a particular situation that you can run into when multiplying these square roots of negative numbers. And the one you have to watch out for is this situation. When you have a pair of square roots with negative radicals inside and they're multiplied by one another, then what you want to do is simplify them first, taking out the I from each one. Alright? You do not want to multiply these two together like so. You don't want to just simply write a square root symbol and then on the inside multiply the negative 2 times the negative 3. You would end up with a square root of 6, which is not the actual answer. Okay, the answer is a minus square root of 6. So you can avoid doing this the wrong way if you simplify it first. Okay, so in this case both radicals are negative, so what we want to do is write this first radical as an I square root of 6, the second one as an I square root of 7. So now that the negatives are gone from inside the radicals, we can write this as a square root of 6 times 7, and the I times I would just give us an I squared out front. In the next step, we would replace the I squared with a negative, and then our square root would become square root of 42. Okay, in the next one, if you wanted to, we do not have both radicals negative numbers. We could multiply it as we normally do. Multiply the two radicals together, negative 8 times 3, under the same square root, and we would end up with a square root of a negative 24. And at this point, to address the negative, we would simply put an I in the front of the square root, drop it from inside now that the I is in the front, and from here you can go about simplifying the square root of 24 using the prime factored form. 2 times 2 times 2 times 3. And so for every 2 of a particular factor we can bring out 1. So this would now become a 2i square root of 6. Alright, and so here we are, example 23. We have again 2 negative radicals. So we simplify first. I square root of 5, I square root of 11, and now we can multiply them together underneath the same radical. 5 times 11. out front we have the I squared. I squared is replaced with a negative, and the radicand becomes 55. So our answer is negative square root of 55. So example 24, our last example of the chapter, we're shown a proof that contains an error. And it must be an error because what's happened here is they've sort of proved that negative 1 equals 1, which is not true. Okay, these aren't the same number. So let's look at how they arrived at this result and try to figure out where the error is. Okay, we have two lines here, and so we're going to examine both of them. What is happening is we're starting with the multiplication of square root of 1 times itself. And what happens is we end up with two different results once we're finished. So these are two separate calculations. This is calculation 1, and this is calculation 2. Okay, now what's happened here is they did not follow the rule that we used up above that said if we're multiplying two radicals, two square roots specifically, with negatives inside both radicals, then we cannot write it this way underneath a single square root symbol, multiplying the negative ones inside. When you do that, you end up with the square root of positive 1, which is equal to positive 1. And so in calculation 2, starting with the same product, they did it the correct way. Square root of negative 1 can be replaced with an I, and so likewise, so can the other one, and we end up with an I times an I, which is equal to I squared, and we've already defined I squared as a negative 1. This is the correct result. So the problem with this proof here is that you cannot calculate the square root of negative 1 squared in this fashion. So that completes chapter 17. Thanks for watching.